special prayer time, I believe, in chapel tomorrow is what I've heard for Professor Hecht, who passed away again yesterday. So I would encourage you to go there to chapel tomorrow and take part in remembering and praying for our community. Today is the last day of class. Lecture 27, the last one. Yay, I'm happy too. I get happy at the end of the semester when things are done. I do have your final exams to write and grade, and yeah, it is a chore for me. It does take me a while, but in the end it's worth it. You know, tests are meant to be learning experiences. They're not just meant to be, you know, assessments. They are meant to be assessments and giving you feedback about how you're doing, but they are also meant to be learning experiences in the studying and even during the test. Though it doesn't feel like it, it can be a learning experience, especially if you put in good work and have success in solving a problem that might seem difficult initially. In Lecture A, we will review what we've done recently with confidence intervals and prediction intervals from section 10.2, as well as the ANOVA analysis of variance regression output for simple linear regression. Sure, we're not going to get to everything there in Lecture A, so there'll be some spillover into Lecture B, as well as reviewing for the final exam in Lecture B. So yes, again, more information about the final, reminding you of things. Actually, I showed you this the last time. It is cumulative, chapters 1 through 10, sections 7.3 and 3.4 we essentially skipped, but pretty much everything else was done to some degree or another. There were parts of individual sections that we skipped, sort of optional subparts you may have noticed as you did your reading that we skipped for sake of time. You can use a whole sheet of paper. Study before you do the whole sheet of paper though, okay? Then you'll know what you're more confident about, what you're less confident about. That will give you wiser choices about what to include on your sheet of paper, front and back, for formulas. You know, these formulas are complicated enough that pretty much everybody's going to want them on their sheet of paper. The standard errors for mu hat, y hat. I'll go ahead and write those down. Again, that's for SE mu hat, that's the standard error S times the square root of 1 over 1 plus, or excuse me, that's the smaller one, so there is no 1 in there. 1 over n plus the ratio of x star minus x bar squared divided by the sum of the xi minus x bar squareds. And the formula for the standard error of y hat is pretty similar, except you have the extra 1 in there, which can make a big difference multiplicatively speaking. This can be many times bigger than that, even though it's just a 1 that's in there. Okay, that would be examples of things you'd probably want in your sheet of paper, okay? Pretty much everybody would need those. We will practice using these today. You want to have your calculator out for that. Calculator will be needed on the final exam for sure. Again, get a good night's sleep and have breakfast before you come. And you can have a snack as well, again, as long as it's not smelly or noisy. Don't cram, again. One more reminder. It's just not a good idea to cram, both in terms of your stress and in terms of your preparation. And the third thing, in terms of your learning. You're going to retain things better long term if you don't cram. All right, let's start by practicing these very formulas here. Actually, we'll practice them on a spreadsheet. But, you know, the exam doesn't have any spreadsheets on it, so you should be able to do these by hand with calculator help. Let's look at the T-bill and inflation example that you had for your electronic homework. This is the full spreadsheet. We used pretty much every formula we knew about regression. Not quite every formula, but pretty much, maybe 90% of the formulas we used in filling out this spreadsheet to see the relationship between T-bills and inflation rates. Treasury bills are, again, government investments, you are giving the money to the government, you're expecting a return. They are borrowing money from you, and they will pay you back with interest. So T-bill returns, that's the interest rate that you get back over various years on average. And inflation rates can be thought of as percentages too. On average, how much do prices go up? You can think of it that way. That also means your buying power goes down for an individual dollar. We calculated all our statistics, our means, our standard deviations, our correlation, our slope, and our intercept of the sample regression line. Added all these columns, x squared column, y squared column, x times y column, calculated the sums of those, SSxx, SSyy, SSxy. We calculated those down here. Found the correlation, confirmed those, and the slope with those alternative formulas, which, again, these are things you should all know for the final exam and be able to use. I have not written the final yet, okay? I will write it, probably some today, maybe some tomorrow. Might not finish it until over the weekend. Hopefully Sunday or Monday I can send you an email with some more detailed information about it. I'm not going to give you all the final exam problems because I'm probably going to reuse some of them. But I will tell you more specifically what to expect. In the meantime, you should practice everything. You should practice a bunch of old exams. Got the y-hat values here from the regression line. Plug in the x values, the inflation rates, into the regression line equation to get the y-hat values. I hope this is all feeling really familiar by now. We've done so much. I hope you're starting to say, I remember what to do. I hope. Calculate the residuals, y minus y-hat, observed value minus predicted value. O comes before P, observed before predicted, observed minus predicted. Some of those are positive, some of them are negative. If the observed value, the data points above the regression line, that's going to lead to a positive residual. Observed minus predicted will be positive. If the data points below the regression line, then the observed values below the predicted value, observed minus predicted, will be negative. But you square them anyway, you do the squared residuals. So those all are positive over here. Add up those squared residuals to get this thing we call SSE, sum of squares of errors. Errors being synonymous with residual. Take again the square root of SSE divided by the degrees of freedom for regression, n minus 2 here, with simple linear regression with one explanatory variable, to get the regression standard error S, which in this case happens to be 1.56787. All right, let's get practice using these. Have your calculator out. Let's pick something for x star and try to find both the confidence interval for the mean of the y's for that value of x star, for the population mean. We don't have population data here. This is just sample data. It's really not a random sample because it was years 2000 through 2008, which are all, one year after the other in the first decade of the third millennium here. It's not really a random sample, though it's sort of random-like, you might sort of say that's typical of what happened overall, but that's probably not completely true. We won't worry about that. Pick an x star, pick a sort of typical kind of inflation rate here. Oh, maybe about 3%. Let's pick that as our sort of typical inflation rate that we're going to think about here. That's going to be our x star. So you have to be given what x star is. Or if you're actually using regression on your own, you have to decide. What do you want to know about? I want to know about T-bill returns in all years where the inflation rate is 3%. Thinking about the future, perhaps. Ideally, we'd have more data from the past than what we have here. So that's going to be our x star. Don't forget the form of these intervals. For the confidence interval, to estimate the mean of the y's, it looks like that for the given x. And for the prediction interval, to estimate the next observed value y for the given x, it looks pretty much the same, it's just a different standard error. It's this other standard error that's going to be bigger than this one. It's easier to pin down the mean than it is the next observed value. There's more variability in the observed values than there is in the mean if we're taking samples. We've got x star then. We've got the degrees of freedom. N was 7, by the way. Or excuse me, 9. N was 9. Degrees of freedom is 7. T star, if I want 95% confidence, with 7 degrees of freedom. You can look it up in the table, back of the book. Ends up being 2.365. The only thing left we have to do is calculate these standard errors. I've got the regression standard error, S. Again, I've got N, 9. I've got my X star, 3. Do I have my X bar? Yeah, it was over here, 2.51. Do I have the summation? Actually, I do. Where is it? So what's the summation here equal to? It's on the screen. This is a real key to know this. Say it again. Where are you getting? Oh, you're getting that from there? That's a guess, but it's incorrect. I'm glad you guessed, though. Any other guesses? It's SSxx. This thing right there, that is the same as what we've been calling SSxx. We've got that on the spreadsheet. What if you were not given that, but instead given the standard deviation of the x's? You can figure that out still. Remember, I wrote this down before. SSxx is also n minus 1 times the squared standard deviation of the x's, which we also call the variance of the x's. Let's confirm that n minus 1, which is 8, times the square of this number, 1.25658, is equal to 11.8226. Let's confirm that. I'll do it right here. N is 9, so n minus 1 is 8. 8 times the square of this number, there you go, you can see it already, is 11.8226. It matches SSxx. That is the same. You do need to know that for the final exam, but you can calculate SSxx that way. Maybe I'll give you SSxx, maybe I won't. Maybe I'll just give you the standard deviation. You have to take n minus 1 times the square of the standard deviation, the variance, to get the SSxx and put it there. Okay? So what I'm saying is real key. That could be on the final. All right, we've got that. Well, I guess we don't have y hat yet. Again, here's the slope and intercept over in cells C17 and C18. Let's find y hat. Y hat for that x star. Taking the slope in cell C17. I'm using dollar signs. I guess I don't really need to, because I'm not going to copy and paste. If I were going to copy and paste, I'd want to use the dollar signs. Times x star, which is in I17, plus C18, which again, I don't have to use the dollar signs here, but I will anyway. 3.445 is your y hat. Okay, let's figure out the standard errors now. Let's do both standard errors. Let's label them over here. SE mu hat and SE y hat. Look at the formula. Get your calculator out and try this with me. I will put it in the spreadsheet, and you can check your answer with the calculator. It would be very good to do that right now. Plug in the appropriate numbers. S is the 1.56787 times the square root. On a calculator, you're probably, if you're doing it all at once, at least you're going to want to use parentheses and ultimately raise to the 1/2 power. I guess there was a square root button too, but maybe you prefer using parentheses and raise to the 1/2 power. We're doing the first one here, 1 over n is 1 over 9, plus x star minus x bar. X star again is 3, it's in cell I17 here, minus x bar. What was x bar? 2.51, I think. Up in cell C13 there, 2.51, that's x bar. Where did I say it was? Cell C13, okay. C13 squared, don't forget to square that. Divide by SSxx. That is the 11.8226. Cell F14. You can try to do it all at once. Looks like the answer is going to be about 0.568. Ideally on the test, though, it's better to do it piece by piece. Calculate this fraction individually first, so I can see what you got for that. Plug in the other numbers. That will help you find any mistakes you might make, and you might get more partial credit. If you just write an answer and it's wrong, can't give you much partial credit, if any. It's just a rounding error, you can probably get partial credit, but you're going to get more partial credit if you show the details. Looks like it's 0.56838 for the standard error of mu hat. I didn't use dollar signs, so I better not copy and paste. I was going to copy and paste and just add a 1, but I didn't use dollar signs, so that would be trouble. SEY hat, once again, S times the square root. This time, don't forget the 1 first. 1 plus 1 over n is 1/9, plus, once again, x star, I'll just type in the numbers this time, 3 minus x bar 2.51 squared divided by SSxx. What was that, 11 something? 11.8226. Looks like that's about 1.6677. Getting that? You trying? Looks like only a few people are trying. You need to practice this. Question?
Would you want to square the 11.826, or is
no,
square
it's
part of that?
the summation, you're summing squares. We've already got the final answer for that. Okay. Ballpark are 3 times bigger. Sometimes it can be 10 or 20 or 30 times bigger, actually. Kind of depending on how big this part is. This square root. How small it is, I really should say. If it's real small, then this one can be many times bigger. And now we're not done. We don't have the interval yet. We have a lower 95% boundary, the left endpoint, and an upper 95% boundary, the right endpoint, for the C.I. and the P.I. Use the formula with plus or minus. You should be able to find the endpoints. For the C.I., it's y hat. The lower endpoint is going to be minus t star times the standard error from u hat. So on your calculator, go ahead and try. First, figure out t star times se mu hat. Figure out 2.365 times 0.56838. Getting something a bit bigger than 1. Subtract that from y hat. Should get about 2.1. That'll be the left endpoint, the lower endpoint for a 95% confidence interval to estimate the population mean of the y's, the inflation. I forgot. It was X, T-bill rate or inflation, I forgot already.
Yeah,
But I remember, that's terrible. X was inflation rate, Y was T-bill. Okay, I can remember that alphabetical order there. 2.1, so we're trying to predict T-bill. The mean of the T-bill return in all years when the inflation rate is about 3%. What's the upper endpoint? Do y hat plus. Oops, that was not good. Undo, undo. It's not undoing. Okay, I guess it did. Was that the same answer I got before? What's right? Y hat plus. Why is it not letting me do the formula there? Equals. Please reload, that's the problem. Okay, here we go. Equals y hat plus t star, don't forget the t star, times se mu hat. Should get about 4.79. So we're 95% confident, based on these data, which is a pretty small sample size, 9, that the true mean T-bill return in all years when the inflation rate is 3%, we're 95% confident that the mean is between 2.1 and 4.8% return. Now again, this is not really a random sample, so this inference we're doing in saying this is maybe a little shaky. You know, the first decade of the 2000s had different economic kinds of conditions than the previous 100 years. I don't know how much you can say about inference in this kind of situation. So you got to think about those kinds of things in real life if you're trying to apply these ideas in real life. Prediction interval is going to be bigger, and in fact probably include some negative numbers, which could then include negative T-bill returns. That's possible. Well, okay, that'd be unlikely, although they are close to 0 these days. Y hat, same Y hat, minus same T star, but now SE Y hat. Try that in your calculator right now. Multiply the T star and the SE Y hat first, then subtract it from 3.445. You get a negative, about negative 0.5. Does include negative numbers. And then Y hat plus T star times SE Y hat gives you about 7.4. So the interpretation there is this. Maybe some economist says, I think with pretty good confidence that the inflation rate next year is going to be about 3%. What is the likely T-bill return between the next observed value of y? Based on this information, based on this prediction interval, we'd be 95% confident that if the inflation rate next year is 3%, or really close to 3%, our T-bill return will be somewhere between negative 0.5% and 7.4%. Okay? Again, if we had a bigger sample and it was truly random, which we may not have for hundreds of years, by the way, it probably would be a better prediction interval. Okay, we're trying to get the idea here. All right, so we practiced those formulas. What about the ANOVA stuff? That can come up on the test too. I think I've got ANOVA stuff in one of these somewhere. Actually, we didn't look at this one before. This is an example from the book, Income versus Age. Well, let's see. Do I have ANOVA stuff in there? I think I got some ANOVA stuff actually in an Excel file. Hang on with me here. Maybe not. I thought I did. Oh, there it is. Okay. Actually, this is a different example. We've never looked at this example in class before, but it is in the book. Looking at the distribution of income and age, income versus age, for different people from age 25 to age 65. It's a lot of data here. Actually, 5,713 data points. Wow. Was it a simple random sample? Maybe close enough. It's It's really hard to do true simple random samples, actually, especially of such big data sets for people over the entire country. Once again, you should be able to read pretty much everything here. There's the correlation, there's the squared correlation, the coefficient of determination. That's S right there. Paying attention, not everybody's looking, everybody should know all these things. That's N, this is S. That's B0, the intercept. This is B1, the slope. These are the standard errors for B0 and B1 that have kind of complicated formulas in the book as well. They're not the ones on the board. Here's the corresponding t-test. We focused on a t-test for the slope. Null hypothesis that the slope is 0 versus the alternative hypothesis that it's non-zero is the main test we've done there. This is the t-statistic for that test. You should be able to calculate that as B1 divided by the standard error. If you took the 892 divided by the 61.76, you could try it right now, you get the 14.44. You should know that. It's a formula. T is B1 minus 0, which I don't bother writing, divided by SEB1. And again, in this case, that's the 892.11 divided by 61.764. Should get 14.44. The corresponding p-values are really super tiny, on the order of 10 to the negative 46, which is so small you can hardly even imagine it. Definitely, we have really strong evidence that the null should be rejected here. Strong evidence that the slope is non-zero, and in fact the slope is positive, so you can also say it's strong evidence that the slope is positive. Here's a confidence interval for the slope, doesn't contain 0, confirming the fact that we rejected the null. All right, again, all things you should know. Be able to read it off this. What about the ANOVA stuff again? Quick review of that, and then we'll take the quiz. Again, n is 5,712. So the n minus 2 that we've always been using in chapter 10 is really the residual df, 5710. This is really the number of explanatory variables, 1, with simple linear regression. If we did multiple regression, which I actually am going to show you something briefly about it after the quiz, and could be bigger than 1, but it's the number of explanatory variables. And these do add together, of course, to give you this one, which happens to be n minus 1, which is the same degrees of freedom for a regular variance and standard deviation of a variable. These are SS's here. You should know this one is our old friend SSE. Sum of the squares of the errors, sum of the squares of the residuals. This one, at the end of class last time, we called SSR. The R there does not stand for residual, it stands for regression. Unfortunately, those both start with an R. Think of residual as error. And this number is SSYY, and it's an amazing fact that if you add up SSE and SSR, though I haven't really told you what SSR is yet, you get SSYY. If you add these two numbers, which are in scientific notation, you get this number. This is 4.7 times 10 to the positive 11th, 1.29 times 10 to the positive 13th, 10 to the 9th is a billion, 10 to the 12th is a trillion. We're on that kind of order. If you add these two numbers together, you get this number. MS stands for mean square. That number, the mean square for regression, MS sub reg, is that SS divided by its degrees of freedom. When you divide by 1, you get the same thing. That's why those two numbers are the same. This one, mean square for the residual, is this SS divided by that number. This number divided by 5,710 is that number. This thing called F is MS for reg divided by MS for residual. That number divided by that number is that. It's very extreme, very large. The p-value there, that's a p-value, is very small. And in fact, in simple linear regression with one explanatory variable, that p-value is the same as this p-value. it's in this table in 2 spots, it's the p-value for the exact same test. We will see in the brief example I show you from multiple regression that those p-values don't have to be the same. When you've got more than one explanatory variable, they're different. They are testing different things. So that's a brief summary of things of the ANOVA part of the table. Let's take a quiz now.